last two lectures we have been addressing the n job m machine flow shop scheduling problem to minimize make span. We looked at the Johnson's algorithm which would solve the 2 machine problem optimally. We also looked at the extension of the Johnson's algorithm where the 3 machine problem the make span can be solved optimally provided the data or the processing times satisfy certain conditions. Now, we also looked at a branch and bound algorithm which we could use to solve the general m machine problem optimally. In particular, we showed an example with 3 machines. We also mentioned that the branch and bound, in the worst case if there are n jobs, then the branch and bound could evaluate all the n factorial possible permutations or n factorial possible sequences before it comes or before it arrives at the optimum solution. So, in the worst case the branch and bound algorithm can do n factorial which means that it will or can do an exponential number of computations. So, when it does an exponential number of computations, the computing time taken to solve the problem optimally becomes very large as the size of the problem increases. So, in such cases it is customary to resort to what are called heuristics or heuristic solutions which essentially do not guarantee optimum. So, in some sense they do not guarantee optimum, so they can be termed as non-optimal methods, but for certain instances the heuristic solutions can be the optimum solutions themselves. The heuristics are capable of giving the optimum in certain instances, but they do not guarantee optimal solutions on all occasions. So, we will now look at some heuristics to solve the general flow shop scheduling problem to minimize make span. But before that, let us also look at one aspect which is regarding this n factorial. Now, if we consider a 2 machine flow shop, which means we have m1 here and we have m2 here, and let us say we have only 2 jobs J1 and J2 which are here. So, since there are 2 jobs, there are 2 sequences possible, which is J1 followed by J2 and J2 followed by J1. Now, let us assume that the processing times for J1 are 6 and 5, which means 6 on M1 and 5 on M2, and processing time for J2 are 7 and 8, 7 on M1, 8 on M2. We have already seen the computation of the completion times and the make span, but let us revisit that aspect once more. So, if we consider the sequence J1, J2, which means job J1 goes first and then followed by J2, we automatically compute the sequence like this. We look at completion times on M1 and M2, let me say completion times here for J1 for J2. So, we would say that J1 first goes to M1 at time equal to 0, finishes at 6, then J1 goes to M2, finishes at 11. J2 enters M1 at time equal to 6, finishes at 13, and then this is available at 11. So, J2 can take M2 at 13, 13 plus 8, 21. This we are very familiar with. We have made an important assumption here that the moment we decide that the sequence is J1 followed by J2, that sequence is maintained on all the machines, both M1 and M2 we have maintained that sequence in our computation. For example, let us look at a scenario where we decide that the sequence on M1 is J1 followed by J2 and the sequence on M2 is J2 followed by J1. So, let me show those calculations. So, we will first look at M1 and then we look at M2. Let us assume on M1 the sequence is J1 followed by J2. So, the sequence is J1 followed by J2 on M1, which means that in M1 we first start with J1, takes 6 time units. So, this comes out at time equal to 6. Now, J2 enters M1 at time equal to 6, therefore, will come out at time equal to 13. Now, let us say on M2 the sequence is J2 followed by J1. So, let me write that on M2 it is J2 followed by J1. So, this would mean that J1 will not immediately go to M2 even though M2 is free, because the sequence on M2 is J2 followed by J1. So, M2 will wait for J2 to be over. So, J2 can access M2 at time equal to 13, and then J2 requires another 8 units. At 21 J2 will come out. Since the sequence on M2 is J2 followed by J1, now J1 can enter M2 after J2 is completed. So, J1, even though it is completed here at 6, will wait till 21, and then it would take another 5 units, and then at 26 J1 comes out. The make span therefore for this order is 26 compared to the make span here, which is 21. Now, if we see very carefully, the flow sharp assumption is not violated. The flow sharp assumption means that every job will visit the machines in the same order. So, even if we look at this schedule or timetable, J1 first visits M1 and then J1 visits M2, J2 visits M1, J2 visits M2. So, the flow sharp assumption is not violated. So, in principle, in the flow sharp, if the flow sharp has M machines, in each machine the n jobs can be sequenced in n factorial ways. So, for each machine it can be done in n factorial ways, and since there are m machines, it can be done the total sequences possible actually n factorial to the power m. But it is not common and customary to use this. It is fairly obvious, making a comparison between this and this. If we retain the same sequence for all the machines, on many occasions we would get better value of the performance measure, such as make span or completion time and so on. For example, the make span is 21, the make span is 26. Sum of completion times is 33, sum of completion times is 47. So, if there were a due date related measure, once again this would perhaps show a higher tardiness than this. So, for what are called regular performance measures, where the performance measure or the objective function will increase when completion times increase, it is better not to follow this and to follow this, where the sequence of jobs is the same on all the machines. This is a situation where the order or sequence of jobs is different on different machines, even in a flow shop. So, it is advantageous to have a situation or to model it in such a manner that the sequence of visit is the same on all the machines. Therefore, we do not consider all the n factorial to the power m, instead we consider only n factorial sequences. So, 1 out of the n factorial will be optimal for the first machine, and the same 1 out of the n factorial now is chosen such that it is optimal when we consider all the machines. So, we reduced the feasible solution space from n factorial to the power m to n factorial. So, those sequences where or situation where we consider the same sequence for all the machines such as this is called a permutation flow shop. So, unless otherwise stated, flow shop would mean a permutation flow shop, and we will not look at non permutation flow shops where the order of visit on the machines are different. So far we have seen only permutation flow shops in this lecture series, and we will continue to look only at permutation flow shops in this lecture series. Now let us go back to the heuristics to solve the problem. So now let us consider this 5 job 3 machine flow shop sequencing problem to minimize make span, and as I have just mentioned, we will consider only permutation sequences and we will not look at non permutation sequence. So 1 out of the n factorial will be optimal in this case. Now we observe, first of all we have to check whether it satisfies the Johnson condition. If it satisfies the Johnson condition, then we could get the optimal solution straight away using a simple algorithm. Now minimum on the first machine is 13, minimum on the third machine is 11, maximum on the second machine is 20. So maximum on the second machine is greater than the minimum on the first as well as minimum on the third, therefore the Johnson condition is not satisfied. So we cannot apply the Johnson condition to try and get the optimal solution to this problem. We may not get the optimum solution if we continue using the Johnson condition and solve it. So let us look at some other heuristic solutions to this problem. Now the first heuristic that we will look at will try and find out a weighted sum for each of these jobs. So we will try and give some weights to each of these machines, and then we try and find a weighted sum for every job. So let us begin with giving a weight of 0 to the machine in the middle, giving a weight of +2 here and giving a weight of -2 for this machine, and then let us try and find out a weighted sum of processing times for each of the jobs. So let us call that as, say let us call W1 as the weight for job 1. So for job 1 the weight will be 16 into -2, which is -32, plus 18 into 0 plus 12 into 2, 24. So 24 minus 32 is -8. Now W2 will be 14 into -2, which is -28, -28 plus 22 is -6. W3 will be 13 into -2, -26 plus 15 into 2, 30, which will be 4. W4 will be 19 into -2, -38 plus 19 into 2 plus 38, 0, and W5 will be 15 into -2 is -30 plus 16 into 2, 32, so it will be +2. So we have now found a weight associated with each job based on the weights that we have arbitrarily assigned to the machines. So it is very clear that if these weights are changed, these numbers will also change. But right now let us assume a standard weight of 0 for the middle, +2 here and -2 here, and then we have computed the weights. Now sort the jobs in decreasing order of the weights, non increasing order or descending order of the weights. So, the maximum is W3. So, J3 comes first, the next one is W5. So, J5 comes second, the third one is 0. So, J4 comes third, the next one is minus 6. So, J2 comes here, and the last is minus 8, J1 comes here. So, this is the sequence that we get if we compute a weight for each job based on a weight given to each machine. Now, for this sequence, let us try and find out the make span. So, we write the completion times for this sequence. We have M1, M2, M3, J3, J5, J4, J2, J1. So, J3 starts at 0, finishes at 13, now goes to M2 at 13, takes another 20, so finishes at 33, now goes to M3 at 33, takes another 15 and finishes at 48. Now, J5 can begin at time equal to 13 on M1, takes another 15, so finishes at 28, has to wait till 33 so that M2 is free, takes another 16, so finishes at 49, M3 is already available at 48, so starts on M3 at 49, takes another 16, so finishes at 65. J4 can start on M1 at 28, so 28 plus 19, it finishes at 47. M2 is available only at 49, so it waits till 49, visits M2, takes another 15 units, finishes at 64. M3 is available only at 65, so goes to M3 at 65, takes another 19 and finishes at 84. J2 starts at 47 on M1, takes another 14, so finishes at 61, waits till 64 for M2, starts at 64 on M2, takes another 10, so 74, waits till 84 for M3, starts at 84, takes another 11, so finishes at 95. Now, J1 starts at 61 on M1, takes another 16, so finishes at 77. M2 is already available at 74, so starts at 77. 77 plus 18 is 95, it comes out. At 95, M3 is available, so starts at 95, takes another 12 and finishes at 107. So, make span associated with this sequence is 107, is the make span associated with this sequence. So, this is how this algorithm works. So, a very simple algorithm, so one pass algorithm where you define weights for the machines. Right now the weights are arbitrary, but there is a logic in this which we will see. Right now the weights are arbitrary, but for any given weight you can calculate an index or a weight for every job. Compute that index and then sort the jobs in decreasing or non-increasing value of the indices to get a sequence like this and evaluate the make span of this sequence, and that gives a heuristic solution. So, this heuristic algorithm will evaluate only one sequence. It could evaluate two if, for example, the some of these indices are equal. So, you could have two or more if some of these indices are equal, but in general it evaluates only one sequence if all the values of these each of these indices is unique. So, it gives a solution with make span equal to 107. Now, one thing that we know is that this 107 need not be optimal. With a bit of luck it could be optimum, but then there is no guarantee that the 107 that we obtained is indeed optimal. So, we need to find out how good it is. Is it good enough or is it not good enough? Now, in order to do that, we also try and find out lower bounds for the make span. We have already seen lower bounds for the make span based on each of the machines. So, we apply those lower bounds to see what we get as a lower bound for the make span. So, lower bound based on M1 is equal to, now let us first find out sum of processing times on all the 3 machines: 16, 30, 43, 62 plus 15, 77, 18, 28, 48, 63 plus 16, 79, 12, 23, 38, 57 plus 16 is 73. So, the lower bound based on each of these is M1 alone requires 77 time units, but then the last job on M1 has to go to M2 and M3. So, the minimum additional time that we require is the minimum of these sums 30, 21, 35, 34, 32, 21 is the minimum. So, minimum additional time required is 77 plus 21. So, lower bound based on M1 is 77 plus 21, which is 98. Now, lower bound based on M2 will be the earliest we can start processing on M2 is the minimum of these, which is 13, because no job can directly start on M2. It has to go to M1 and then only it can start M2. So, the earliest M2 can begin is the minimum of these numbers, which is 13. M2 itself requires another 79, and then the last job on M2 also has to go to M3. So, it requires at least an addition, which is the minimum of these, which happens to be 11. So, the lower bound will be 13 plus 79 plus 11. So, this will be 13 plus 79 plus 11, which is 79 plus 11 is 90, 90 plus 13 is 103 is a lower bound based on M2. Now, lower bound based on M3 is no job can start on M3 directly. So, any job that the first job on M3 should have visited M1 and M2. So, the earliest M3 can begin is these two sum to be minimum. So, this is 34, 24, 33, 34, 31, 24 is the minimum, plus it requires a 73. So, lower bound on M3 is equal to 24 plus 73, which is 97. Now, out of the 3 lower bounds, the maximum one is the best bound. So, 103 is a very good lower bound that we have got from using the 3 machines. So, now we have 2 pieces of information. We know definitely based on the lower bound that the make span cannot be less than 103. So, the make span can only be 103 or more. Now, we also know from here that since we have the optimum make span can be 103 or more based on the lower bound. Based on this, we already have a feasible sequence with a make span of 107. Therefore, the optimum make span can only be 107 or less. So, the goodness of this will be, H minus L by L into 100%. Now, we assume the worst case, the optimum is the lower bound, which is the worst case, and therefore, if the optimum were 103, then the goodness of this is 107 minus 103 divided by 103 into 100%. So, this is 4 by 103 into 100%. So, this is, let me say, approximately 4% or less than 4%, 3 point something percent, we would say 4%. So, if we are willing to accept a solution which is the worst case is 4% above the optimum, the reason the worst case 4% comes because you do not know that if this optimum is more than L, actually this should be H minus O by O, heuristic minus optimum by optimum. Since we do not know the optimum, we substitute it with the lower bound. So, the optimum is 103 or more, therefore, the actual goodness will be 4 or less, because this can increase and H minus L can actually decrease. So, in the worst case it can only be 3 plus something. So, if we are willing to accept a solution which is within 4%, then we can comfortably take this and we need not worry about trying to get to the optimum. But on the other hand, we would like solutions which are better than this. Do we have sequences which have make span less than 106? In such a case, then we can look at other heuristic algorithms and try to see if we can get solutions which are less than 106 make span. Now, this heuristic is called the Palmer's heuristic or Palmer's algorithm, and was developed by Palmer in the year 1965. Even though these values of -2, 0 and +2 appear arbitrary, there is a rationale in choosing these values. If we see very carefully these sequences J3, J5, J4, J2 and J1, they were based on a decreasing order of the index. Now, J3 had the highest value of the index, while J1 had the lowest value of the index. Now, if you see these, J1 it is very clear it got the lowest value because this 16 is bigger than 12, and J3 had a higher value, positive value, because this 13 was smaller than 15. Now, for a 3 machine problem we have put a 0 here. So, whatever is there on the second machine does not matter, only what is there on the first and third machines matter. So, if a job has a higher processing time on the third machine or on the last machine and a lower processing time on the first machine like J3, it will have a higher value of the index. Another job which has a higher value on M1 and a lower value on M3 will have a lower value of the index and therefore figure later in the sequence. J3 which has a lower value on M1 and higher value on M3 will have a greater than 0 and a higher value of the index, and therefore will figure early in the sequence. Now, this is very close to the Johnson idea that if we go back and see the rule, the machine that has the smallest number on M1 will appear from the left, which means it will appear early in the sequence, while jobs that have smaller values on M2 will appear from the right, which means it will appear later in the sequence. That essence is captured by the weights. In principle, that essence is captured by the weight. So, the principle should be the middle one has a certain weight, the ones to the right, generalizing it to a 5 machine or a 6 machine problem, the one that comes to the right should have positive and increasing weights, and those to the left should have negative and decreasing as in this. The absolute weight will be high, but because of the negative it will be decreased. Then we fit this algorithm into the Johnson principle, which works. But then there are a couple of limitations here. because we put a 0, then the second machine is not contributing at all. And then there are a few other questions like, should this be 0 or should this be some constant, some other thing other than 0. Now, should these be the same? So, all these questions can come, but essentially the principle behind computing this index is based on the Johnson idea. Now, what happens when I have an even number? If I have 4 machines, what do I do? So, the suggestion was -3, -1, +1 and +3. There is no middle machine. So, the 2 middle ones will get -1 and +1, and then a +3 on this side and a -3 on the other side. So, there were several improvements to this algorithm, but the most important contribution or 2 things associated with this algorithm is that it is a very early algorithm, one of the earliest, and the very idea of the weights and the index captures the essence behind the Johnson's algorithm. Now, let us go to another algorithm. Let us simply retain this solution somewhere, and let us write this solution here, which is J3, J5, J4, J2, J1 with make span equal to 107. Now, let us go back to another algorithm and see what we do. Let us also write that our lower bound is 103 that we have. Now, when we started, we checked the Johnson condition and we said that this does not satisfy the Johnson condition, so that it definitely gives the optimum solution. Still, we could have used the same algorithm, because if it had satisfied the Johnson condition, then we would have created an equivalent 2 machine problem, and then we would have solved the 2 machine problem optimally using Johnson's algorithm. Now, it does not satisfy the Johnson condition, but nothing prevents us from applying that rule to see what we get. So, let us try that. So, let us now create an equivalent 2 machine Johnson problem by adding. So, this becomes M1 plus M2, this becomes M2 plus M3, J1, J2, J3, J4 and J5. So, this becomes 34, 18 plus 16, 18 plus 12, 30, 24, 21, 33 and 35, 34, 34 and 31, 32. So, now we make the Johnson sequence for this. The smallest one is 21, so J2 goes here, this goes. The next smallest one is 30, so J1 comes here, 30. The next smallest one is 31, so J5 comes here. The next smallest one is 33. So, J3 comes here, 33 is on the first machine, so it comes from the left, and the only one available is J4. So, when we apply the extended Johnson's algorithm for the 3 machine into this, knowing fully well that it will not or may not give the optimum solution, we get a sequence like this. Now, let us find out the completion times for this sequence. So, CT is here. The sequence is J5 first, J3, J4, J1, J2. Now, the make span associated with this is J5 starts at 0 and finishes at 15. At 15 it goes to M2, comes out at 31, 15 plus 16, 31. At 31 it goes to M3, takes another 16 and comes out at 47. Now, J3 is the next one. So, J3 starts at 15 on M1, this 15, takes another 13, so comes out at 28, has to wait till 31 for M2 to be free, takes M2 at 31, finishes at 51, 31 plus 20, by which time M3 is free. So, 51 plus 15 is 66. Now, J4 comes third, M1 is available at 28, so starts at 28, finishes at 28 plus 19, which is 47, waits till 51 for M2 to be free, goes to M2 at 51, takes another 15 and finishes at 66. Now, exactly at 66 M3 is free, so it takes M3 and then takes another 19 and finishes at 85. J1 can start at 47 because M1 is free at 47, takes another 16, so 47 plus 16 is 63, waits till 66 for M2 to be free, goes to M2 at 66, takes another 18 and then comes out at 84, but M3 is available only at 85, so goes to M3 at 85, takes another 12 units, so comes out at 97. Now, J2 is the last job, it can go to M1 at 63, starts at 63, takes another 14, so finishes at 77, waits till 84 for M2, takes another 10, so 94, waits till 97 on M3, takes another 11, so gives us a solution with 108. So, the make span associated with this sequence is 108. Right. So, what we have done right now is we have simply applied the Johnson's extension algorithm to a 3 machine problem and created an equivalent 2 machine problem with M1 plus M2 and with M2 plus M3. Now, if we go back and revisit what we did in the Palmer algorithm, we essentially put a 0 weight on M2, which means we looked only at M1 and M3. So, nothing prevents us from actually using the Palmer idea again into it and take only M1 and M3 and try and get an equivalent 2 machine Johnson problem and apply the Johnson's algorithm on it. So, right now we will look at only with M1 and M3, let us formulate another 2 machine problem here. Only with M1 and M3, let us formulate a 2 machine problem with this. So, once again J1, J2, J3, J4 and J5. So, we get 16, 12, 14, 11, 13, 15, 19, 19, 15, 16. Now, let us make another Johnson. The smallest one is 11. So, J2 on the second machine. So, comes from here J2. The next smallest is J1, once again from the second machine. So, J1 comes here. The third smallest is J3, which is on the first machine. So, J3 is here. The next smallest is J5, which is here, and then J4 comes here. So, let us quickly find out the make span for this sequence. So, we write M1, M2, M3, J3, J5, J4, J1, J2. So, very quickly writing the completion times. So, J3 is 13, 13 plus 20, 33, 33 plus 15, 48. J5 starts at 13, finishes at 28, waits till 33, finishes at 49. M3 is already available, 49 plus 16 is 65. Then we have J4, starts at 28 plus 19, finishes at 47, waits till 49, takes another 15 which is 64, waits till 65, takes another 19 and finishes at 84. J1 starts at 47, takes 16, finishes at 63, waits till 64, takes another 18, so 82, again waits till 84, takes another 12 which is 96. Now J2 starts at 63, takes another 14, finishes at 77, waits till 82, takes another 10, 92, waits till 96, takes another 11 which is 107. So what we have done in this algorithm is, now we get another solution whose make span is 107. So between these two solutions we could pick the one which is better, which has 107. So we essentially did two solutions we evaluated in this algorithm. So one of which is for a 3 machine. The first one we did was a Johnson problem with M1 plus M2 and M2 plus M3 based on the Johnson extension. The other is we did only M1 and M3, and we took the best out of the two, and therefore we get another solution with J3, J5, J4, J1, J2 with 107 again. So we did not get a solution better than Palmer, but then we got the same solution as Palmer based on this, but we got a different sequence in this. Now for 3 machines we got 2 solutions and we picked the best. Now can we generalize it to M machines? So if we have M machines, we call them M1, M2, MM. Now we create M minus 1 sequences. For 3 machines we created 2 sequences. For general M machines we create M minus 1 sequences. So let us call sequence S1 as M1 and MM. Take the first machine, take the last machine, do a Johnson out of that, which is this. The second one S2 will be M1 plus M2 and M minus 1 plus M. Take the first 2, add, take the last 2, add, do a Johnson out of it. The third sequence will be M1 plus M2 plus M3 and M minus 2 plus M minus 1 plus M. Take the first 3 and add, take the last 3 and add and do it. So as we keep doing, the last sequence S M minus 1 sequence will be M1 plus M2 plus M minus 1. This will be M2 plus M3 plus M. So take the first M minus 1, take the last M minus 1 starting from 2 and get it. We do not find the mth sequence because that would mean you add all of them both sides, so you will get the same. So we do not do that. So for a general M machine problem, you generalize it to find M minus 1 sequences. So, if I have 10 machine problem, irrespective of the number of jobs, I will evaluate 9 sequences based on these 9. Somewhere if each of these has a tie in the Johnson, you could get more sequences, but if you have m machines, we will end up doing m minus 1 sequences and take the best out of that. So, in this case, in a 3 machine case, we had 2 sequences and we took the best. If you had 8 machines, then you would have 7 sequences and you would take the best. Now, this is still a heuristic algorithm. Now, this heuristic algorithm is commonly called as a CDS algorithm, stands for Campbell, Dudek and Smith. Who are the 3 authors, and this came in 1977, and a very popular algorithm for use to find out the make span for a general m machine flow sharp sequencing problem. So, also generally based on lot of experimentation, it is observed that this algorithm gives better solutions than the Palmer's in general. Palmer's would still evaluate only one sequence, CDS would evaluate m minus 1 sequences and choose the best. Now, let us look at one more heuristic algorithm and then we to see whether we can get a solution which is better than 107. So, the goodness is once again 107 minus 103 by 103. So, we have not made too much of an improvement. For this particular example, the CDS gives the same value of the make span as that of the Palmer. Now, we look at one more heuristic very quickly, and what we do here is that we start with, let us find out the sum of processing times of each of the jobs. So, 16 plus 18, 34 plus 12, 46, 14 plus 10, 24 plus 11, 35, 13 plus 20, 33 plus 15, 48, 19 plus 15, 34 plus 19, 53, 15 plus 16, 31 plus 16, 47. So, now we arrange the jobs in decreasing order of the total processing time. Decreasing would always mean non increasing order of this. So, the highest is J3, the next is J5, I am sorry, the highest is J4, the highest is J4 with 53, the next is J3, the third is J5, the fourth is J1 and the fifth is J2. Now, we take the first two of these, which is J4 and J3. So, take so step 1, take J4 and J3. Now, J4 and J3 can be permuted in 2 ways, which is J3 J4 and J4 J3. It can be permuted in 2 ways, J3 and J4. When I say take the first two, we are taking J4 and J3, not necessarily in that order, J4 and J3, not J3 following J4. So, if we take only J4 and J3, there are 2 jobs and they can be permuted in 2 ways. Now, find out the make span for the partial sequence J3 J4 and J4 J3. Let us just do that. So, for J3 J4 it will be 13, 33, 48, J4 is 13 plus 19, 32, 33 plus 15, 48, 48 plus 19, 67. For J4 J3 it is 19 plus 15, 34, 34 plus 19 is 53, 13 plus 19 32, 34 plus 20 54, 54 plus 15 69. Now this partial sequence has a make span of 67, this partial sequence has a make span of 69. So choose this sequence. So now choose J3 J4, step 2. So step 2, choose J3 J4. Now take the next job here, which is J5. Now J5 can be squeezed in 3 ways. J5 can come here, J5 can come here, J5 can come here. So you could have 3 sequences which are J5, J3, J4, J3, J5, J4, J3, J4, J5. Now find out the make span for all these 3 partial sequences like we did here and choose the best. So one of them will be the best. At the moment we are not going to show the computation, but one of them will be the best. If for some reason let us say that this is the best for the purpose of argument after the computation, then look at the next one J1 and squeeze it in 4 positions. It could come here, it could come here, it could come here, it could come here. So then evaluate 4 more sequences, choose the best and take the last one and squeeze it in 5 positions and then evaluate the best out of these 5. So at the end we will have 5 sequences and we will choose the best out of these 5 sequences. Now if we continue with the algorithm, then we finally get a solution . 3 4 5 1 2. So we finally get a solution 3 4 5 1 2. Let us compute the make span for this. So we would have M1, M2, M3, J3, J4, J5, J1 and J2. Now let us quickly compute the make span. So first one is J3, so 13, 33, 48, followed by J4, 13 plus 19, 32, waits till 33, finishes at 48, goes at 48, finishes at 67. J5 comes next, 15, so 32 plus 15, 47, waits till 48, takes another 16, 64, waits till 67, takes another 16 and finishes at 83. Then comes J1, starts at 47 plus 16, 63, waits till 64, 64 plus 18, 82, waits till 83, takes another 12 and finishes at 95. J2 starts at 63, takes another 14, finishes at 77, waits till 82, takes another 10, 92, waits till 95, takes another 11 and finishes at 106. So the make span here is 106, which is better than the 107 that we got. So we have a make span of 106. Now this algorithm is an insertion algorithm. And this insertion algorithm for make span is called the NEH algorithm, stands for Nawaz, Onscore and Ham algorithm, which came in the year 1984. Now this insertion algorithm is found to work very well for make span minimization in a flow chart, and it has been shown to give on an average slightly better results than the Campbell Dudek and Smith algorithm. Now if you have m machines and n jobs, CDS will evaluate m minus 1 sequences and will choose the best. NEH in the end will evaluate n sequences and choose the best. And usually in all flow sharp problems n is greater than m. So, NEH algorithm would actually evaluate more sequences than the CDS algorithm, either because of that or otherwise it is able to perform slightly better than the CDS algorithm when we consider the make span minimization. Now that we have a solution with 106, then the goodness will become 106 divided by minus 103 by 103 into 100%. Now this is of the order of 3%, whereas with 107 it was of the order of 4, slightly less than 3. This will be slightly less than 4 in the earlier case and slightly less than 3 in this case. So, if we are happy with a solution which is within 3% of the optimal, we can take the NEH and use it. If not, we proceed for other methods with the hope that we may get or we wish to get a solution with less than 106. But then it depends on where the optimum is, and for this particular problem instance optimum is 106 and therefore NEH has given us the optimum. But then we do not have a way to know that, so we would still say that NEH has given us a solution which is within 3% of the optimum. So, we have now seen some heuristics to solve the make span minimization problem in a flow sharp. Earlier in our discussion on sequencing and scheduling, we started with single machine, flow sharp and then job shop. So, we will look at some aspects of scheduling in a job shop in the next lecture.